Earth observation can help us plan and develop renewable energy resources like solar and wind power. The decision to build wind farms depends on knowledge about geography and weather. Jay Perlman from Boeing explains.
So you not only want to know if the wind is strong enough to power it, but you also want to know the risks involved. If the wind is over the ocean, as in a marine wind energy site, it can be relatively smooth. If it's on a mountaintop, and you see many if you go around the world of turbines on mountaintops, they're put there because you think the wind is stronger. But because the wind is going up mountains and down mountains and turning around mountains, it's very turbulent, and that reduces the life of the turbines. Are there roads? Do you have access to the site? Are there power lines to bring the power for distribution? What are the demographics? Is there a heavy population or is it a sparse area?
Satellite observation makes it possible for scientists to link atmospheric research to practical problem solving.
We've spent quite a bit of time in developing a program at the University of Colorado that's devoted to climate and climate variability and its impacts on water, particularly in the western Intermountain region. One of the things that we worked with is with the Colorado River managers in actually laying out a decision tree or a decision calendar. And this was very important because it put down a structure of when a water reservoir manager has to make certain decisions for operating the reservoir versus when they can think of planning opportunities where weather and climate information would be helpful. And also it looks at opportunities for where you might be able to manage the reservoir not just for agricultural purposes, but for purposes that would sustain the ecosystem or the river system in general.
We don't understand really right now how the land surface interacts with the atmospheric system. And that's because we've never had any global observing systems which have been able to monitor soil moisture over the globe over extended periods of time. It's critical because if we get a perturbation in the system, say if we get a very dry period, what we see is we see a persistence of this, and this is what becomes a drought. And that is that something starts it, but then it feeds itself because there's no moisture evaporating from the surface, building up clouds which produce rainfall. And so when you see a drought develop in some regions, it just persists because we just don't have the moisture there in order to bring the rainfall that's needed. The same thing can happen with floods. If you get a perturbation in the system and you start getting too much water in a particular area, you get feedback into the atmospheric processes, and then this persists into extended periods of flooding and rainfall in a region. And both of these, of course, have impact upon agriculture and the crop yields, which we worry about a lot.
From remote sensing, we've really learned a few different things. Primarily how to track a lot of the plumes from fires, from forest fires. We see exceedances of air quality that we, before satellites, we'd have some rough association that there was a transport event associated with fires, but with satellites we can actually pinpoint the location of those fires and determine its tracking and movement to specific receptor locations.
Earth observation technology is helping scientists to understand how the atmosphere works to produce the fresh water needed to sustain life.
The amount of water in the sky, the amount of fresh water in the sky that actually replenishes the water in the ground is absolutely tiny. It's barely measurable relative to the rest of the water on our planet. CloudSat is all about studying that fresh water in the sky, how it gets formed, where it gets distributed, how much rains fall from the sky from these clouds. And we think this is absolutely critical for understanding the water usage and water supply of the future, particularly since that future is about to be influenced by the pressures of climate change. CloudSat flies a really unique radar and operates at a very much higher frequency or very much smaller wavelength than typical weather radars. With this new radar we can actually quantify the amount of water in the clouds. The radar is kind of an indirect weighing device. It actually weighs the water content of the clouds, and that water content tells us about how much rain forms, tells us about how much sunlight's reflected to space, how much energy flows in and out of our planet that sustains our climate system.
Over time, remote sensing provides us with information not only to develop models, but also to challenge them.
Perhaps the most important area of satellites is the way we do air quality management and planning. We use very comprehensive three-dimensional gridded air quality models. Those models work in fully three-dimensional space over large time periods, over multiple pollutants. It's very difficult to evaluate those models and to get the sensory or the actual observational input for anything above the ground. Satellite systems help in an enormous way, because now we can actually challenge the models to actually fully characterize what's going on in the vertical structure of the atmosphere in a manner that we couldn't have done before.
Earth observation continues to support important scientific research. This knowledge helps us monitor, understand, and model how Earth systems work together. Olaf Niemann, a Canadian scientist, focuses on applications in forestry.
Most of our work is in British Columbia. We work on Vancouver Island quite a bit, which is where we're located. But we're also working in the interior of the province, and many of these areas have been heavily impacted from pine beetle, mountain pine beetle, and the health of these forested environments has been seriously threatened by these beetle infestations.
Earth observation involves people from many disciplines.
You've got people working, for example, in atmospheric science, oceanography, studies of life, biologists. You've got people working in solid earth geophysics. You've got people working in sensors, which is where I work, sensor development, a whole range of disciplines. And in fact, it's probably one of the key areas these days in science where we're bringing people together. It's a crossroads, quite frankly, in science.
Earth observation is an evolving enterprise. As we launch more satellites with more sophisticated remote sensing technology, we continue to collect and analyze data for scientific inquiry and practical applications.
4, 3, 2, 1. We have ignition, and we have liftoff of NASA's Calypso.
Remote sensing technology will continue to evolve and improve. The greatest challenge will be to apply what we learn and work with technology across international boundaries.